But unit 9 is current electronics. In there will be resistivity, conductivity, Ohm's law, and simple circuits. And then finally, RC circuits, where things actually get interesting. So it's a broad category. And up until this point, we've talked about charges, and we've talked about the flow of charges. This is going to be a little different because we're finally going to have a discussion that involves active circuits where something is happening. We've kind of lied a little bit about what we've been doing so far. Our circuits have just kind of instantaneously gone from no charge on a capacitor to having a charge on a capacitor. And that's not really how a circuit works. There is time involved. So I'm starting with the end, actually, by drawing an RC circuit. A circuit that has both a resistor and a capacitor in it. And I'm starting here because we are familiar with capacitive circuits. This little squiggly line is the symbol for a resistor. And what a resistor does will become quite evident in a minute, or probably in a day or two. But the squiggly line can have several different shapes to it. I'm not doing a good job. They should all be the same kind of peak. This is one way to draw the squiggly line. This is for a constant resistance. But there's also sometimes things that look like this. This would be a variable resistor, something where you could change the amount of resistance by maybe turning a dial. So there are other symbols for resistances that don't look like resistances. Light bulbs have a symbol that looks kind of like this. It's a couple of loops inside a closed bulb, because the idea is that a light bulb has a filament. The filament has resistance, but it gets hot enough to burst into flames. So we put it inside a glass ball and we evacuate the air, or we fill it with some kind of inert gas so it can't catch fire. But that's what a light bulb will look like. But it also acts as just a standard resistance. In fact, your first lab is going to be dealing with just little light bulbs and stuff. And then there's, that should be enough. This is good enough to get us started. And you know what the symbol for a capacitor is. So in the circuit, I have a switch, I have an EMF, I have a resistor, and a capacitor. In the past, we close the switch, and we'd say that the capacitor is going to have charge on it after we close the switch. That's not really what happens. When we close the switch, immediately upon the switch being closed, there's an electric field everywhere in the wire. Please hear this, and please write these little things down. Immediately when the switch is closed, there will be an electric field everywhere in the wire. This has the effect of causing a force on all the charged particles that are in the wire. People tend to think of the wires as empty, but when they first come to electronics, that's not the case. It's not an empty hose. This is a wire that is filled with electrons, already there. So the moment we close the switch, a charge exits the battery and pushes all of the charges around the circuit instantaneously. And a charge enters the battery the same time a charge exits the battery. Now, that doesn't mean that the circuit acts instantaneously. It's not like the electric field did something weird and the charges in the battery have made it through the circuit. What has happened is that the battery has moved the charges that are already in the wire. And what I want you to write down is that what this suggests is that the charges begin to move, and their rate of motion is called current. Current is the rate at which charges move, dq dt. All right, so I ended by defining current as dq dt. Now, there's a couple things about this that I won't say defy logic, but are definitely don't feel appropriate, don't feel like they're the right way to go, but it's not up to me. We use a lowercase I, or I will use a lowercase I, to usually describe currents that are not constant. And I'll usually use an uppercase I to define currents that are constant. I'll try to be consistent there, but not always. I'll do my best. The book and the AP exam will not, but I will try to. It's the rate at which current passes a point. It's not a velocity. I want to be really clear about this. It's not like how fast the charges are going. We'll get to the idea of the movement of charges later. It's just how much current passes a single point in the circuit in a certain amount of time. So that's going to be in coulombs per second. Which is named the amp after Louis Ampere. Now, so I want to take a moment here to talk about resistance and the difference between a resistance and a resistor. Just like before with a capacitance and capacitor, a resistor is a device. It is a thing. Resistance is a measurement. And resistance is defined somewhat redundantly. So we define resistance as how much current you can get to flow based on your applied voltage. But we don't say it like that. I think this is reversed, but it's because of the way we deal with resistance. So if you'll notice, it's how much voltage is applied and how much current you get to flow, but not current based on voltage. So it's a reverse, but we can't actually do that. What I mean is voltage is something that's set up by a device. It exists with or without there being a flow of current. A battery can have voltage and have no current. A device can have resistance and have no current passing through it. So voltage and resistance can be created separately and don't have to be around each other. The truth is, current is created when we apply a voltage across a resistor. Current is drawn from a battery and is created at the time of a circuit. It can't exist without there being a voltage and something in the wires to draw it out. But since resistance is measured as how much resistance there is to the flow of charge, as opposed to the opposite of the word, which would be conductance. Resistance and conductance are inverses of each other. Conductance would tell you how easily charge passes through a material. So resistance is the reverse of that, which is how hard you have to push to get something to go through a material. Higher resistance, less current for the same applied voltage. In fact, this relationship has been given a name, Ohm's law. What we say is that Ohm's law works for ohmic devices. That's circular reasoning, just to be sure. In fact, in your equation sheet, Ohm's law will be written kind of a ridiculous way, like this. V equals IR. Somewhat ridiculous because it doesn't show true dependence. Voltage does not depend on current and resistance. Again, voltage is established separately. You can build a battery and have no current. You can build a resistor and have no current, but current is created when you place a resistance across a potential difference. So I want to be very clear, although this is called Ohm's law, it does not have the proper dependence. The proper dependence is this one. Current depends on voltage and resistance. Now, I want to be very clear about Ohm's law. Ohm's law works for for devices that have standard resistance. And unfortunately, we define something as having resistance as a device that obeys Ohm's law. Do you see the circularness in that reasoning? So there's no easy way to say this. Most devices obey Ohm's law for a small amount. Plastic, wood, bits of your skin, yarn, they all can have a certain range in which they obey Ohm's law, but most devices don't fully obey Ohm's law. I mean, most things eventually don't obey Ohm's law. So we say that the materials obey Ohm's law. We say that usually within a range of currents do they obey Ohm's law. Once you get outside that range of currents, most devices no longer obey Ohm's law. For example, a light bulb. If you measure the resistance of a light bulb using an ohm meter, these exist. An ohm meter is nothing, and your multimeters are ohm meters. They can measure resistance. If you measure the resistance of a bulb without it being connected to a circuit, and then measure its properties when it is connected to a circuit, you'll find that its resistance isn't the same. And that is because once the bulb is connected and lights up, it gets hot. And once something gets hot, its resistance changes. Most objects change their resistance depending on their temperature. So Ohm's law really only works for a narrow range of A, devices, and B, temperatures. Now, resistance is measured in ohms. And the symbol for an ohm is the Greek letter omega, just a little horseshoe. The unit of the ohm is volt per amp. Now, you guys are smart people, super smart. I'll give you 30 seconds to tell me what this is in Coulomb, M, K, and S. 29, 28. I look at that and I don't see anything, do you? When we break these things down to our Coulomb meter, kilogram seconds, they don't really have much to show, do they? It's hard to see where it came from. The measure of resistance is the ohm. It's probably best to remember as a volt per amp. But there's stuff in here, and I want you to have seen it, even though it took way too much to drag this out of you. Remember, volt is kind of a measure of energy. It's energy per unit charge. An amp is the flow of those charged particles. That's what it is. That's how those things are related. So measuring ohms is measuring how much a bit of material, an object, will resist the flow of charged particles. Something with a lot of resistance gives you very little current for the same voltage. Right? Do you see how that works? If I take the same battery and apply it to two objects, the one that produces the least amount of current has the most resistance. That should make some intuitive sense just with the way you guys have used the word resistance in the past. To resist is to try and prevent. So we measure kind of conductivity in reverse. We measure conductivity by measuring how much something resists the flow of charged particles. Well, that was rougher than I thought. That's okay, though. What kind of circuit is this? This is a series circuit. Do you think a series circuit would have more resistance or less resistance than the resistors by themselves? By putting them in series,
Why Siri? I'm not sure why Siri just started.
neither am I. But I'm glad to know that Siri's always listening over there. And by saying Siri like 6 or 7 times, maybe when somebody's watching a stupid video, all their devices in their house will start going off. Just like say something, hey Siri, turn off the lights, and all of a sudden the lights in their house go out. Be hilarious. All right, look, if you put resistors in series, I don't know if you guys can predict whether that would increase the resistance of a circuit or decrease the resistance of a circuit. But if you're thinking about it from the flow of electrons, the electrons have to go through both of them, don't they? So I think we probably could anticipate that the total resistance of a circuit might increase due to having resistors in series, but we should be able to prove it. And I don't mean that arbitrarily. I showed you how to use Kirchhoff's rules to figure out how voltage would be dealt with in a circuit. So we could use Kirchhoff's rules here. There's got to be a voltage drop across each of these devices. And if I draw the appropriate loop through the circuit, one in which I'm going from the negative side to the positive side of the battery, then I probably could write this as the EMF minus the voltage across one resistor minus the voltage across the other resistor equals 0. Now, I'm confident that if I asked a few of you to do this, maybe one or two of you would have no trouble because you've been paying close attention. And this is going to be shockingly condescending, but some of you don't remember what we did just last week or the week before. But when we did this last time, we brought in the definition of capacitance to try and see if we could figure out kind of what the circuit looked like to the battery. Meaning we would reduce this down to what we feel the equivalent resistance is. To try and determine how our circuit behaves. You should be able to mimic that process. I don't have a lot of high hopes, though, based on us just asking what a Newton was and having difficulty getting that out of the room. So I will say that this shouldn't be a big surprise. If I use Ohm's law here, V1 would have to equal I1 times R1. This is how we use the capacitance formula. And V2 would have to equal I2 times R2. And for this single circuit, we could probably say that the EMF would have to equal I total times R equivalent. That all seem reasonable to you? All right, good. So that suggests I could write this as I total R equivalent minus I1 R1 minus I2 R2 equals 0. Let's see. Should pick somebody here. Hey, Blake, how many junctions are in this circuit? How many places does the current split up in going from one side of the battery to the other? Doesn't split up. There's no junctions in this circuit. Because there's no junction in the circuit, there's never a place where the current could split up. There's never a place where the current can split up. That would suggest that there's only one current passing through this circuit. That is Kirchhoff's second rule, correct? The junction rule. If there's no junctions in any point on our circuit, any place that we choose, the current into that point has to equal the current out. That suggests that I total equals I1 equals I2. There's no junctions. In fact, I'm just going to call this I. If I sub that in over here, I'll get IR equivalent minus IR1 minus IR2 equals 0. Factor out the i's, solve for R equivalent. Seems like a pretty okay rule for series, doesn't it? That the total resistance of a circuit that is comprised of resistors in series will be the sum of the resistors. So you put resistors in series, the total resistance goes up. Makes perfect sense. Those electrons have to go through two different devices that are both in series. It has to be pushed through them both. Total resistance of your circuit goes up. So I'll give you, 3-4 minutes to apply that logic here. You've seen it done. I would like what the equivalent resistance must be here. So like write a V1 here and a V2 here?
Yeah.
Okay, can you give me an appropriate Kirchhoff's equation for this circuit?
Like E is equal to V1.
All right, E is equal to V1. Sounds great. Can you give me another one?
E is equal to V2.
All right, excellent. Jasmine, can you tell me something else I can do here? How about this? Is there any junctions in this circuit? Excellent. So can we write a Kirchhoff's second rule equation to maybe monitor that junction? Which junction do you want? I only see two junctions. I see a junction here and a junction here. So do you want to deal with junction A or junction B? All right. So you'll have to come up with some, way of writing this, but what do you want to say about junction A? Kirchhoff's second rule says that current in equals current out. So I see a junction there where there's a current going maybe this way. And then at the junction, current continues to go this way. Wouldn't you agree? And current also goes this way. Does that make reasonable sense? Let's just give those some names. For example, what do you think we should name this current? That sounds reasonable. Goes through resistor 1. Let's call it current 1. How about this one? Excellent. And maybe this one? Okay. So now I need to come up with a rule for those using Kirchhoff's law. So how could we write that as an equation? What's that? All right. So Kirchhoff's second rule says that current in equals current out. So if this is our junction right here, I see one arrow pointing into that junction, current 3, and I see two currents leaving that junction. So that'd be current 1 plus current 2. That's how we'll use the junction rule. Now, it seems to me that it's current 3 that's passing through the battery. You guys all okay with that? All right, so we've got a lot of pieces here. I think we're gonna have to bring in stuff like V1 equals I1 times R1. That all seem okay to you guys? And maybe V2 equals I2 times R2. In this case, what I'm going to do is also say that the EMF equals I3 times the equivalent resistance. That seem okay to you guys too? All righty. I think the best thing to do here is to use this one, as it seems like the right place everything's being substituted into. It brings all the currents together and all the voltages together. So if I do that, I'll get the EMF over the equivalent resistance for I3 is going to equal, let's see, V1 over R1 for current 1. plus V2 over R2 for current 2. What?
Yeah.
Put it all together first,
So you know how you did EMF equals.
because there's a clearer path, is these are all equal, right? The EMF equals V1 equals V2. They're all the same voltage. They're in parallel. Things in parallel have the same voltage. It's not a surprise. That's a consequence of Kirchhoff's rules. So I think I can just say all of these are the EMF. And should that be non-zero, that means since what we're getting at is a way of writing the equivalent resistance for our circuit, I think trying to get the equivalent resistance is our goal. Does this not look familiar to something we've already done? I mean, this is exactly what we did for capacitance, right? Almost point for point. That's why it's a little frustrating sitting in this chair, because we did this already. But I will say, if you're paying close attention, you will notice that it's the opposite for resistance as it is for capacitance. Resistors in series, you sum the resistance. Capacitors in series, you have to deal with the inverses. Capacitors in parallel, you just add the capacitance. Resistors in parallel, you have to deal with the inverses. You guys see it? It plays by a different set of rules, especially since resistance is inversely related to the current, where capacitance isn't. There's no current passing through a capacitor. It's based on charge. So that brings us to at least one point where I'd like to sum some things up. Voltage equals current times resistance. This is Ohm's law. Resistors in series are just summed. And resistors in parallel we add the inverses. So these are going to be similar. There's one striking difference. In a capacitor circuit, the capacitors get charged, but the capacitor is still an open circuit. No current passes through the plates of the capacitor. In a resistor circuit, there is current passing through the resistor. So a resistor does not store energy. As the electrons pass through the resistor, what's actually causing resistance is collisions. The electrons are bumping into things. The voltage is like pressure. It's pushing the electrons through. Current is the flow of charges. The resistor is trying to prevent that flow of charges. So the electrons are bouncing into things. This is going to consume energy. And that's what resistors do. They consume energy. The most basic resistor consumes energy in the form of heat. They just get hot. But you can have more complicated resistances that use the energy of the electrons passing through them. An electrical device can be boiled down to a resistance in the manner in which it consumes energy. We call the consumption of energy power. Power is the rate at which energy is consumed, or the rate at which work is done. A course in mechanics would talk about the rate at which work is done. We're going to be a little flexible here. We'll say either the rate at which work is done or the rate at which energy is consumed. Now, we'll get more into power as the year progresses, but this is going to be work over time, or joules per second, which from last year, most of you guys should know, is the watt. Joule per second. So the next time I ask you what a joule is, you should know. And now if I ask you what a watt is, you should know. I'm going to state this without proof, that power equals I squared times R. You should probably realize there might be more than one way to do this, right? For an ohmic device, can you see another way that you could calculate power? There are two other ways. You get 30 seconds to find them. I figure 2 more people. All right, Tin, give me one of them.
Power is equal to I times V.
Sure, that'll do it. So, Mary, can you give me another one? What's that? Well, you see Ohm's law there, right? We're going to try and eliminate I in this one. So probably going to do some subbing in of V over R, where I is. Can you do that for me? Yep. All right. Not terrible. Let's see if we can do a few more things here real quick, just so that we kind of put all the things together. We now could talk about energy consumption in a circuit. This was similar to calculating how much energy was stored in a capacitor circuit. But now we're talking about energy consumption. They're different. This is happening over time, so it's telling you how much energy is being consumed each second. But as long as the circuit is connected, it is using energy, not storing energy. We have a way of calculating the total resistance for a system in series and a way of counting the total resistance for a set of resistors in parallel. When we consider a set of resistors in series, what must be true regarding the current for resistors that are in series? Say again? That's right. Current must be the same for all resistors in series, the same way that the charge was the same for capacitors in series. That should make reasonable sense based on Kirchhoff's rules. So, if I have a parallel element in a circuit, what's a reasonable assumption about the resistors that are in parallel? Say again? The voltage, that's right. For resistors that are in parallel, the voltage should be the same. That suggests that we could do our standard kind of stepwise reduction for resistors, just like we did for capacitors. Give it a shot. Can you solve this circuit? I don't believe I have to give you any, to teach you. I think we've done this. You will be applying some new rules.